This is the divergence theorem. It says, if R is a three-dimensional region and it's bounded by a surface, then this is true. So here's my region R, and I'm going to draw it like this, because I can't draw stuff in 3 dimensions. And this notation means the boundary of R and since R is a 3D region, this is a surface. It's like a 2-dimensional object, right? It is a 2-dimensional surface living in 3-dimensional space. In other words, like a sphere is a 2-dimensional surface living in 3D space. But the ball inside the sphere is a 3-dimensional solid in 3D space, or a 3-dimensional region. So the boundary of a 3-dimensional region is a 2-dimensional surface. If I have a 2-dimensional region, we saw that the boundary of a 2-dimensional region was like a 1-dimensional parametric curve, right? 1-dimensional closed curve. But in this case, again, we're just reducing the dimension of our, what do you call it? We're reducing the dimension of our manifold by equating this triple integral to a double integral. So if capital F, my vector field, has a positive divergence, that means the vector field lines are kind of pointing away. And that means there's like a positive flux happening across that surface. And so if I integrate the entire 3D solid, and the integrand is the divergence of this vector field, it's the same thing as adding up all of the flux across its boundary. So more divergence inside the solid means more flux across the boundary. More flux across the boundary must mean there has to be more divergence inside the solid. And so the negative divergence would just be the same thing with the arrows pointing in the opposite direction. And that's really what this is saying here. Questions about what the divergence theorem says? Super clear? Okay, verify the divergence theorem for the following vector field and 3D region. So when it says verify the divergence theorem, what that means is write the divergence theorem. And to verify this, we've got to solve both sides of this equation and make sure the left side is equal to the right side. And of course, we know it's going to work, right? I mean, it's a theorem for a reason. We have credible sources telling us that this is a theorem. That means it's always going to work. But the purpose of this question is so that I can see every step. And obviously, you can check your answer. If you do both sides of this integral equation, they should be equal to each other. If they're not equal to each other, then you know you made a mistake and you can go back and fix it. But let's talk about the left side. I'm taking a surface integral of a vector field on the boundary of R. What is R? What shape is it, Garrett?
Circle. Or
A cylinder. There we go. This is a cylinder. Because this is saying that the radius of my cylinder is 2, and then the height of my cylinder is 3. So it's a cylinder centered at the z-axis, centered at the z-axis, with a height of 3 and a radius of 2. Okay, so the entire boundary is going to be 3 different surfaces, right? One of these surfaces is going to be the bottom of the cylinder. What would the bottom of the cylinder look like? I think I'd be better off doing the bottom of the cylinder in polar coordinates. I need F dot product with the you got to remember your surface integral formula. Dot product with what? It's the cross product of the partial of r with respect to u and the partial of r with respect to v. R d theta. And so we use the lowercase r in the in our formula for the surface integral to mean like the parametric surface. That's different from this lowercase r, which is the polar coordinate variable r. Different r's. Okay. And then we would let theta go from 0 to 2 pi, and r go from 0 to 2. And we will eventually try to parameterize this. Like the bottom circle, or the bottom disk of this cylinder, is going to be a parametric surface. So there's going to be 3 entries in this vector. And parameters u and v are going to be I don't know, maybe I should make the parameters the same as kind of like polar coordinates. I'm going to let u go from 0 to 2, and v is going to go from 0 to 2 pi. That way, u is kind of like the r in polar coordinates, and v is kind of like the theta. And the way I would parameterize the x, y, and z coordinates of the disk would be 0, because we're at the bottom of the cylinder for the z. And the bottom of my cylinder is at z equals 0. And then the x coordinate would be u times cosine of v. And the y coordinate would be u times sine of v. Okay, so this lowercase r is different from the polar coordinate r. This lowercase r is describing to me what is my parametric surface. My parametric surface gets 2 parameters because it's a 2-dimensional space. U is going from 0 to 2 because my radius of my cylinder is 2. V is going to be like the theta here, and it's going to go from 0 to 2 pi, so I get a full rotation. The x coordinate along my surface is going to be u times cosine of v, and the y coordinate is going to be u times sine of v. The z coordinate is 0 because this is the bottom of my cylinder. Then I'm trying to decide on what I should use for notation. I'm also trying to decide how I should kind of parameterize this next part. Because this is going to be the lateral surface of my cylinder. Lateral surface. And for the lateral surface of my cylinder, how do I want to describe that space? I would say I like the idea of a z coordinate, and then the other would be like a theta. I would have like a theta and a z. So this is going to be 2 cosine, let's call it theta. I don't know why I didn't just use theta to begin with. And this is going to be 2 sine theta. And then this is just going to be z, because why not? So theta gets to go from 0 to 2 pi, and z gets to go from 0 to 3. And I'm going to go back here and fix this. I'm going to make the u's and the v's just r's and thetas. But the difference is that the z changes on the lateral surface, but what's fixed is the radius. The radius is always 2 on the lateral surface of my cylinder. And then the third part of this surface integral this would be like d theta dz. I think I need the r because I think it's actually taken care of in this whole part. And then dz goes from 0 to 3, d theta goes from 0 to 2 pi. The last part is going to be a lot like the first one, because now I'm going to deal with the top of my cylinder. And so again, I'm going to have dr and d theta. But this is going to be the top of the cylinder where the x-coordinate is going to be r cosine theta, the y-coordinate is going to be r sine theta, and the z-coordinate is now 3. R goes from 0 to 2, and theta goes from 0 to 2 pi. So the boundary of my cylinder has 3 parts: bottom, lateral, top. We broke it into 3 surface integrals. And I have to first describe those surfaces as a parametric surface, where I give my my x-coordinate, my y-coordinate, and my z-coordinate in terms of my parameters. This time I use parameters r and theta, theta and z, r and theta. I need to come up with a better symbol to use for my parametric surface, so I don't have to use the lowercase r. Because if we're going to use lowercase r for polar, I don't want to use the same symbol for my surface. So maybe I'll think about that before next year. And come up with a nice Greek letter or something. Okay, so let's solve these integrals. Ru, that is the partial of this vector with respect to, and I'm not using u, that's just the placeholder for the name of a parameter. I guess I'm using r. Rr is going to be cosine theta, sine theta 0. And r theta is going to be Derivative of cosine is negative sine. Derivative of sine is cosine 0. And so the cross product between these two is going to be 2, 3 minus 3, 2. That's 0. And then 3, 1, 1, 3 is 0. And then 1, 2, 2, 1. So 1, 2 minus 2, 1. That's cosine squared plus sine squared. That's 1. That's just r. 0, 0, r. That is the cross product here between these partial derivative vectors. So here, I can rewrite that double integral from 0 to 2 pi, 0 to 2. Of my capital F vector field dot product with this cross product. So capital F dotted with 0, 0, r. Are we following? No? Are you eating a grapefruit?
Yeah, I'm trying to.
Okay. Explains why maybe we're not following, but here's F dot with this cross product, the 0, 0, r. So the first two entries don't matter in capital F, right? It's only the third entry that matters. And that should make sense, right? Because we're talking about the bottom of the cylinder, which is completely flat in the xy plane. So if I'm trying to add up the flux through the surface, the only part that adds flux to it is the part of the capital F vector field that's vertical, the vertical component poking through the bottom surface. And so yeah, that's why only the third entry in capital F is going to matter. And we look at capital F, the third entry is z squared. So I can write z squared r. That's supposed to be a 2. It's supposed to be an r. Z squared r dr d theta.
We don't have to add the extra r.
No. I'm like 99.0% sure that we don't have to add the extra r. Even though this looks like polar coordinates, because I'm again pretty darn sure that the cross product between those partial derivatives already takes into account the sort of stretching and squishing of the geometry that happens, if that makes sense. I think whenever you do these partial derivatives and then you take their cross product, I think that already accounts for the fact that it's going to give you smaller chunks near the z-axis and larger chunks away from the z-axis. And I think that's why you end up with this whole thing being proportional to r, so that r is smaller near the z-axis and bigger farther away from the z-axis. I think that's kind of built in. It's like baked into this formulation. Now, that is hopefully a straightforward integral to do. It looks like I have constant bounds, and so I can even, oh, I need to plug in, what is z? What the heck is z? Z is 0, isn't it? In my entire parametric surface, the z coordinate is just 0. So where it says 0 squared, that's a 0. That is an easy integral. It's as easy as it gets. And while we're in this mode of thinking, let's look at the top surface, because it should be a really similar problem to think about. Let's take the partial with respect to r. And then again, I would get cosine theta, sine theta, 0. And the partial with respect to theta, again, I'm going to get negative r sine theta, r cosine theta, 0. And so since I have the same partial derivative vectors, I'm going to get the same cross product. I'm still going to get 0, 0, r for my cross product. And that means I'm going to end up setting up the same double integral. And the difference here, when I get to this point, is that z is no longer 0 at the top surface. What's z equal to? At the top surface, z is equal to 3. So that's going to be 9 times 2 pi times the antiderivative of r with respect to r at 0 and 2. And so that's 9 times 2 pi times 2, which is like 36 pi. So I've got 0 flux across the bottom surface. I have 36 pi flux through the top surface. And again, that makes sense to me anyways, because my vector field has a vertical component in the z direction of z squared. And if z is 3, then I've got a vertical component of 9 going through the top surface, and the top surface is flat. And so there's like a 9 of flux going through the top surface of my cylinder. The last thing we have to do is consider the sides of my cylinder, which is the lateral surface. And we're going to do this integral to figure out the amount of flux going through the lateral surface of the cylinder. Now, the partial with respect to r is, sorry, I don't have r as a parameter anymore. I have theta and z this time. So let's take the partial with respect to theta. And we get negative 2 sine theta, 2 cosine theta, 0. And the partial with respect to z is 0, 0, 1. And the cross product between these is going to be 2, 3, 3, 2, which is going to be 2 cosine theta. Three, 1 minus 1, 3, so negative 2 sine theta. And then 1, 2, 2, 1, so 0. My cross product vector is going to be 2 cosine theta, 2 sine theta, 0, if I did the cross product right. So let's set up the integral. Got this integral from 0 to 3 and 0 to 2 pi of capital F dot product with 2 cosine theta, 2 sine theta. Let's go get my capital F vector. And this is the capital F vector. When I do the dot product, there is a 0 in the third entry of this cross product vector, so I don't care about the third entry in capital F. All I care about is that the first entry is going to be 2x times 2 cosine theta, and the second entry is going to be negative 2y times 2 sine theta. 2x times 2 cosine theta is going to be 4x cosine theta. And then minus 2y times 2 sine theta, so minus 4y sine theta. d theta dz. Okay. I need to replace the x and the y in this integrand here and here with x is 2 cosine theta and y is 2 sine theta. Yep. So replacing the x and the y, is going to be 4 times 2 is 8 cosine squared theta minus 8 sine squared theta d theta dz. I don't see any z's anywhere. There's no z's in the integrand, there's no z's in the bounds, so I'm just going to multiply by 3 and take out that outside integral. And then I can take out an 8. And I'm integrating from 0 to 2 pi of cosine squared minus sine squared. Does anybody know any good trig identities for cosine squared minus sine squared? I know this because I was just talking about this at 8 a.m. with my Calculus 1 class. But cosine squared minus sine squared is cosine of 2 theta. Cosine of 2 theta gives you cosine squared minus sine squared. And now we take the antiderivative of cosine, and the antiderivative of cosine is sine of 2 theta. And then I have to divide by a half, chain rule and everything. And then I plug in 2 pi and I plug in 0. What is sine of 0? 0. What's sine of 4 pi? 0. And in this case, for the lateral surface of my cylinder, it's not that there's no flux happening at the surface. I think most parts of the surface do have a lot of flux happening from the vector field capital F through the surface. But together, it's symmetric. It like cancels each other out. There's just as much going in to the lateral surface as there is going out of the lateral surface. So when you add up the total net flux through the lateral surface, it's 0. So to take the full surface integral, I have to add up 0 plus 0 plus 36 pi. So the total surface integral over the boundary of R of F is going to be 0 plus 0 plus 36 pi. There's no flux happening through the bottom surface. There is flux happening on the lateral surface, but it cancels each other out. N equals out. There is also flux happening on the top surface. And there's more going out than going in on the top surface, so you get 36 pi just from the top surface. Okay, questions so far? The next thing we're going to do, since this question asks us to verify the divergence theorem, is now we're going to do the integral on the right side of this equation. And if we do this correctly, and we've hopefully done the first integral correctly, then this should be equal to 36 pi, according to the divergence theorem. So now let's take the divergence of this vector field, and then we'll take a triple integral over that divergence over the region R. And I really hope I don't have to erase anything. I hate doing that. But let's take the divergence of F. Do you remember divergence? It's kind of like the, quote, dot product between the gradient and the vector field. So I'm thinking about adding together the partial of the first entry with respect to x plus the partial of the second entry with respect to y plus the partial of the third entry with respect to z. So what's the partial of 2x with respect to x? You're right, that's 2. What's the partial of the negative 2y with respect to y? Negative 2. What's the partial of z squared with respect to z? 2z. So in other words, the divergence of F is 2z. Now we set up a triple integral in a way that's going to cover this region R, and my integrand is going to be the divergence of F. And the region R, I think, is best described with cylindrical coordinates. So here I am going to use the r, dr, d theta, dz, or whatever order of integration you choose. Z gets to go from 0 to 3. Theta goes from 0 to 2 pi. r goes from 0 to 2. I don't see any thetas anywhere, right? There's no thetas in the bounds. There's no thetas in the integrand. So I'm just going to multiply by 2 pi. I'm going to take that 2 outside of the integral. And then I've just got the integral from 0 to 3 of 0 to 2 of z times r dr d theta. Sorry, dr dz. In fact, I can simplify that further to just be 4 pi times the integral from 0 to 3 of z dz times the integral from 0 to 2 of r dr. So it's 4 pi times 1/2 3 squared and 1/2 2 squared, which is 36 pi. Was it easier to do the surface integral or the triple integral? Easier to do the triple integral? So sometimes this could be a use case for the divergence theorem. If you're taking a surface integral over a closed surface, then you can consider just taking the divergence of your vector field and doing a triple integral instead, and maybe that saves you some time. Depends on how it's, depends on what the solid is, if it has good symmetries, blah, blah, blah. But that's the idea. Questions? No questions? All right. Find the volume of the 3D region bounded by the following parametric surface. So that's our familiar torus parametric surface. And now we want to find the volume. I think we found the surface area of this on Friday, but now we're going to find the volume of it. And here's a trick for finding volume. If I give you capital F equals x thirds, y thirds, z thirds, what is the divergence of F? Yeah, Carter, why is that divergence 1?
The partial derivatives for each of the components of f is 1/3.
Yeah, the partial derivative of x thirds with respect to x is 1/3, the partial derivative of y thirds with respect to y is 1/3, and the partial derivative of z thirds with respect to z is 1/3, so the divergence is 1. We like that because if I were to take a surface integral over the boundary of a region R of the vector field, that's going to give me the triple integral over the region of its divergence. And that would be just a triple integral with the integrand of 1 using this capital F vector field. And so that would be the volume of R. So this is one way I can calculate the volume of a solid. I could take the surface integral over its boundary of this particular vector field. It's kind of a roundabout way of doing things, but you could do it. So I think, I mean, wouldn't have put this in my notes if it weren't possible. I think you can do this example. You can find the volume using a surface integral of this vector field. So we've already got the parametric surface set up for us. And I'm supposing that the volume of R is going to be this surface integral and that parametric surface is going to be 0 to 2 pi, 0 to 2 pi. The capital F vector is x over 3, y over 3, z over 3. And that has to be dot product with the RU cross RV, du dv. So here's RU. The partial of this with respect to u is going to be negative sine of u, 3 plus cosine v. Cosine of u, 3 plus cosine v, and 0. RV, which is the partial derivative of this parametric surface with respect to v, is going to be negative sine of v cosine u, and then negative sine of v sine u, and then the partial with respect to v is going to be cosine v. So what about their cross product? Their cross product is going to be 2, 3 minus 3, 2. So 2, 3 is going to be cosine u, cosine v, 3 plus cosine v. I'm going to write it out somewhere else. Cosine u, cosine v, 3 plus cosine v. And then 3, 1, 1, 3. So negative cosine v sine u. No, it's two negatives make a positive. And then 3 plus cosine v. And then the third term in the cross product is going to be 1, 2 minus 2, 1. And 1, 2 is going to be sine squared u times sine of v times 3 plus cosine v. It's going to be a long one. I'm going to have to write it. Sine squared u sine of v, 3 plus cosine v, minus, so that was 1, 2, and now we need 2, 1, so minus a negative, that's going to be positive. 2, 1 is going to be cosine squared u sine v. Three plus cosine v. But this simplifies a lot. Looks bad now, but I guess the first two entries don't simplify. I get cosine u, cosine v, 3 plus cosine v, cosine v, sine of u, 3 plus cosine v. And then the last one, sine squared plus cosine squared is 1. And so I get sine v, 3 plus cosine v. Okay, so maybe it doesn't simplify a lot. I thought it would simplify more. It doesn't. But that's the idea for the cross product. Then we're going to take the dot product of that with the x thirds, y thirds, z thirds vector. And that's going to be our new integrand. So the dot product between this and x thirds, y thirds, z thirds is going to be x over 3 cosine u cosine v 3 plus cosine v plus y thirds cosine v sine u 3 plus cosine v. You know, I'm just going to factor out the 3 plus cosine v because that's going to be a common factor between all of these guys. Might as well factor that out. du dv. Now we've got to plug in the x and y and z. What are x and y and z on this parametric surface? Well, x is cosine u times 3 plus cosine v, y is sine of u, 3 plus cosine v, z is sine of v. So let's plug those in for x, y, and z and see what we get. Can also factor out a 1/3. And so again, the x is I want to say cosine u. Yeah, cosine u. So this is cosine of u times 3 plus cosine v. Yeah. Times cosine u cosine v plus, and the y is going to be sine of u times 3 plus cosine of v, and then the z is sine of v. So that's me plugging in x, y, and z as definitions. Okay. Now do we see anything that cancels? How do I simplify?
Is there a cosine squared u plus sine squared u?
Yeah. I'm going to factor out cosine v 3 plus cosine v, and that way I'll get cosine squared plus sine squared, and that's just 1, so that can collapse a little bit. And I'll get 1 times cosine v 3 plus cosine v. Plus sine squared v times 3 plus cosine v du dv. And I think I'm going to use the fact that cosine squared plus sine squared is equal to 1. So that way I can write 3 plus cosine of v Well, let me think about this for a second. Because I can make that squared, but then does that actually help me?
Could you distribute the cosine b? That way it'd be cosine b squared, or cosine squared b plus sine squared b, and you can make it 1, 2.
Yeah, that's right. Yep, that's the right way. Connor got it. Great job. Very nice. So then we would end up with 3 cosine of v plus cosine squared v plus sine squared, and cosine squared plus sine squared is 1 times 3 plus cosine v du dv. And then I imagine we want to FOIL that. And in FOILing, we will find that we got rid of all the u's for one thing. Right? There's no u's anywhere. No u's in the bounds, no u's in the integrand, so I can just multiply by 2 pi. And that just gives me one integral. And then I can FOIL and say first gives me 9 cosine v. The last is going to give me 1 cosine v, so that's going to be a total of 10 cosine v's. Plus the inner gives me the number 3, and then the outer gives me 3 cosine squared v dv. And I can solve those 3 terms separately. Like in the case of 10 cosine v, the antiderivative would be 10 sine v. And if I plug in 2 pi or 0 to sine, that just gives me 0. So the first term doesn't matter, right? When you take the definite integral of the first term, everything goes to 0. So I've got like 2 pi over 3 times 0 for the first term. 3, the antiderivative is 3v, and I plug in 2 pi and I get 6 pi. And then for the last term, cosine squared is the same as 1/2 1 plus cosine of 2v. And so that's going to be integral from 0 to 2 pi of 1/2 plus the integral from 0 to 2 pi of 1/2 cosine 2v dv. That is, and don't forget about that 3, but 1/2 v times 2 pi, 1/2 times 2 pi is pi, plus antiderivative of cosine sine. So it's going to be 1/4 sine of 2v. Oh, but you know what? The signs of integer multiples of pi go to 0. So I get a pi, or a 3 pi, because don't forget about that 3. I get 3 pi plus 6 pi is 9 pi. 9 pi times 2 pi is 18 pi squared. 18 divided by 3 is 6 pi squared. Is that right? Nine pi times 2 is 18 pi. 6. Yeah, that should be 6 pi squared. And that's the volume of my torus. What a wild problem. Let's look it up. Check our answers. Inner radius. That's not what I want. Inner radius, outer radius. I want the radius of revolution. Let's make that 3 meter. And then the tube radius, I think, is 1 meter. 1 meter. So the volume of the torus should be, not in cubic inches, cubic meter, 59.22, okay? What is 6 times pi squared? 59.22. No. Just downloaded a virus. But I think we got the right answer. Yikes. But, we were actually able to do that problem. And if I had tried to do a triple integral, I don't know if I would really understand how to describe the area that we're integrating very well. I mean, maybe you could do it with a little bit of work. But in any case, this is one way you can calculate the volume of something weird. And so you can use the divergence theorem with this vector field, because it has a divergence of 1.
How did you get F?
I made it up. And actually, there's more than one F that has a divergence of 1. Right? That's not the only choice. I chose this F because it gave me a nice divergence of 1. And I wanted the divergence to be 1 because a triple integral with the integrand of 1 will give you the volume of the region you're integrating. But there's actually a bunch of choices. Any F vector field that has a divergence of 1 will work. Like, those are both completely valid choices because they have a divergence of 1. And so if I do the surface integral with 0z, that would also work. That might actually even be easier and faster for all I know. I just haven't tried it like that.
So we find the volume of your divergence has to be 1.
Yes, to find the volume, when you do the surface integral method with the divergence theorem, you want the divergence of your vector field to be 1. How much time do we have left? We've got 13 minutes. Yeah, so it'd be a fun exercise, I think, maybe for you guys, is to like go home and see if you can rework this problem with 0z. And it might be easier. I say it might be easier because when you take a dot product between the capital F and the cross product of your partial derivatives of your whatever, we had this really long expression that came from x thirds, y thirds, and z thirds. But if you plugged in 0z, well, now these terms go away, and you just get z sine of v, which is just sine squared of v. And that might be a really fast way to do the same integral. Maybe it doesn't take as much work if you do that, right? Maybe it's easy. Stokes' theorem. Just like Green's theorem and just like the divergence theorem, this is a way to reduce the dimension of your manifold. It's saying that you've got some surface in space, and it doesn't have to be flat in the xy plane, but you can have some old wavy surface in space. And if I took a path integral counterclockwise around this boundary of the surface through space, so I give a parametric curve that describes the boundary of the surface, then a path integral of the vector field is going to be equal to the surface integral of the curl of that vector field. So imagine inside the surface, you're measuring the curl. How much does this vector field swirl around? And you're adding up all of the swirliness of the vector field in this surface. How much it's swirling is going to contribute to how much the counterclockwise traversal of its boundary aligns with the vector field. It's really hard to find a use case for Stokes' theorem. This isn't very useful. I can give you problems where I say verify that Stokes' theorem is true and make you work out the left side with a path integral and make you work out the right side with a double integral of the curl, but it's not super duper duper useful. One thing that you could potentially do is you could say, I want to calculate the following surface integral over the vector field F. So I've got a surface integral of F, and there's two ways to calculate this. I could do this. We could choose G so that F is the curl of G. And then I could do a path integral instead of a surface integral. And that's like one possible use case of Stokes' theorem, but it's pretty limited because it's kind of hard to find a vector field G so that F is the curl of G. That's not an easy thing to do. And then even then, you still got to define what the boundary of your surface is and that kind of thing. So we may not actually work this problem in class because we're running out of time. That's one kind of possible use of Stokes' theorem.
Is there a way to take an integral of a vector in, because like the curl of F is going to end up as a vector. Is there a way to integrate it in that form?
So it's a good question. Like, G is a vector field and F is a vector field because the curl of a three-dimensional vector field is a three-dimensional vector field. And so choosing G so that F is the curl of G means that like I want F to be, what's the curl formula? The partial with respect to Y of G3 minus the partial with respect to Z of G2. And the second entry would be the partial with respect to Z of G1 minus the partial with respect to X of G3. And the third entry is the partial with respect to X of G2 minus the partial with respect to Y of G1. And so the best way to do this is guess and check. Let's say G is equal to, and I need the first entry to be a Y. So maybe I make the partial of G3 with respect to Y equal to Y. I can make it 1/2 Y squared and make everything else 0. Does that work? Because that would be Y for the first entry. And then any other mentions of G3, just with respect to X, and that's it. Yeah, so this is one example of choosing a capital G so that F is the curl of G. And then that way, if you know this boundary is just the unit circle in the xy plane with radius, or sorry, not the unit circle, a circle in the xy plane centered at the origin with radius 3, and you can parameterize the counterclockwise traversal of that circle as 3 cosine t, 3 sine of t, 0. And then you take that path integral of this vector field, and it's going to be, well, it's going to be 0 because the path is only in the xy plane, and this is have no component in the horizontal directions. It only has a vertical component. So I don't know. There's a lot more I would like to say, but I feel like we're out of time. I feel like this is like a wrap on the whole Calculus 3 course, right? Because when we come back from break, we're going to have a test on Monday. We're having a final exam review day on Thursday. And so I'm out of time to continue to tell you about math. I know. We'll sprint to the finish here. But, this is relatively easy to find capital G because capital F is a simple vector field. If capital F was a really complicated vector field, it'd be harder and harder and harder to find G because you're talking about solving 3 partial differential equations simultaneously. That's not an easy task in general. One last thing I want to tell you about is this idea of Stokes' theorem. And I think the next idea, if you wanted to take, some kind of advanced math class that I'm not going to offer because this is not my field of specialty, but there's like a generalized Stokes theorem. And the generalized Stokes theorem looks really cool, I think, in the way it's notated. And it looks like this. But each one of these symbols is kind of packed with a lot of stuff to interpret. What generalized means is we're not just talking about specifically 2-dimensional surfaces and their 1-dimensional boundary. We're not specifically talking about 3-dimensional regions and their 2-dimensional surface boundaries. We could be talking about 4-dimensional regions and their 3-dimensional boundaries, or 5-dimensional regions and their 4-dimensional boundaries, or regions of 2025 dimensions and their 2024 dimensional boundaries. And it applies. So instead of writing a whole bunch of integral symbols, we just write one, and it's implied that you use as many as you need, and that there would always be one more integral on the right side of this equation than the left. The little partial derivative symbol tells you that this is the boundary of S, and this is the region S. And this little partial derivative symbol refers to what's called the exterior derivative of the vector field F. So here's my vector field F, and here's the exterior derivative. The divergence is an example of an exterior derivative, and the curl is an example of an exterior derivative, but the idea of exterior derivative can be generalized beyond 3 dimensions. So you can take exterior derivatives in like higher dimensional space. And it's in this sense that the boundary of a surface is kind of like taking a derivative. That's why we use the little partial derivative to represent the boundary, is because taking the boundary of a surface is kind of like taking the derivative of what's happening.